Hello students, welcome to EPG Pathshala. I am Dr. Varun Vyas from Department of Physics and Astrophysics, University of Delhi. Today we are going to talk on a module Hall effect, that is Hall probe and measurements under the paper Characterization of Materials Part 1. After completing this module, a student will be able to understand Hall effect in metals and semiconductors, Hall effect, that is Hall effect measurements by van der Pauw method. Hall effect was observed for the first time in 1879 by Edward Hall. He proposed that as electric current flows through a specimen kept inside a magnetic field, a voltage develops across the sample. The magnitude of this voltage is proportional to the current as well as the magnetic field, while its direction is perpendicular to the directions of both current and magnetic field. The effect is termed as Hall effect and forms the basis for several applications as well as devices. For example, magnetic field meter, Hall effect multiplier, and motion detectors. With the experiments, the Edward Hall successfully determined the sign of the charge carriers in the conductor for the first time. Presently, the Hall effect is extensively used in measurements such as whether the given specimen is a metal or a semiconductor, carrier concentration, mobility of charge carriers, magnetic flux density, and finally to measure the signal power in electromagnetic waves. In fact, the principal motivation for exploring Hall effect towards better understanding the electrical properties of materials comes from the failures of simple model of metallic conductivity to explain the measurements performed by Hall effect. Hall effect. Let us assume a slab of a conducting material as depicted in figure 1. Let L be its length along x-axis, W be its width along y-axis, and T its thickness along z-axis. Assuming conductor has Q is equal to charge, which may be either positive or negative or both, but here we will be considering single sign. N is equals to density of charge carriers in brackets or the number of charge carriers per unit volume, and Vx equals to drift velocity of the charge carriers when current Ix flows in positive x direction. Drift velocity is the average velocity of the charge carriers with which they transfer the conducting material of application of external electric field. Without application of any external field, charge carriers possess random thermal motion in the conductor, such that there is no net transfer of carriers along the length of the conductor. However, when electric field is applied, there is a net transfer of carriers along the conductor's length. Current Ix can be obtained by the product of current density Jx and the area of the cross section of the conductor Wt. Moreover, Jx is the product of the charge density and the drift velocity Vx. Thus, the current can be expressed as Ix is equals to Jx into omega t. This is equals to N into Q into Vx into omega t. This is represented as equation 1. Current Ix across the conductor is induced by the electric field Ex applied along the conductor's length. When the current scales directly with the electric field, the material is said to be obeying the Ohm's law, usually expressed as Jx equals to sigma into Ex. This is represented as equation 2. Here, the sigma represents the conductivity of the material of the conductor. Suppose a magnetic field acts perpendicular to the plane of this conducting slab. The Lorentz force, that is QVB, acts on the charge carriers and deflects them along one end of the slab. This deflection causes charge carriers to accumulate near one side of the slab, thereby creating a transverse electric field EY, counteracting the force due to magnetic field. When the strength of this counter field is sufficient to balance the force by the magnetic field, there is no net flow of carriers along y direction. This can be written as Ey is equals to Vx into Bz. This is represented by equation 3. Here, Ey is the electric field, also termed as the Hall field along y direction. Bz is the magnetic field along z direction. The Hall voltage developed Vh along the conductor is equals to negative integral of Vy into dy. This is equals to Ey negative of Ey omega. This is represented as equation 4. Equations 1, 3 and 4 yield Vh is equals to negative of 1 by Nq into Ix in Bz divided by T. This is represented as equation 5. 1 by Nq term is often described as the Hall coefficient Rh. That is, Rh is equals to 1 by Nq and is represented as equation 6. The sign of the Hall coefficient depends on the type of carriers such that it is positive for positive charge carriers and negative for negative charge carriers. Practically, the sign of the carriers is determined by the polarity of Vh. The SI unit of Rh are m cube divided by c, or commonly m cube divided by a minus s. The Hall effect in metals and semiconductors. In practice, the charge carriers often encounter some resistance while traveling through a material. The resistance to the flow of the charge carriers arises from scattering of charge carriers from other charge carriers, impurities, or lattice vibrations. Any applied field accelerates the charge carriers. However, it might lose its energy due to scattering. If the average time between the successive scattering is tau, then on an average we have a retarding force which acts on the carriers and is given by F retard is equals to minus mv divided by tau. This is represented as equation 7. Here, m represents the mass of the charge carrier under the impact of the applied electric and magnetic fields. Newton's second law becomes m into dv by dt is equals to q, or in brackets, e plus v into b brackets close minus mv by tau. This is represented as equation 8. Here, v represents the average velocity of all carriers. Under steady state conditions, time derivative of v becomes 0, following the convention of b pointing towards z-axis and setting left-hand side of the equation 8 to 0. This yields Vx is equals to q tau divided by m into Ex plus q tau divided by m into Bz into Vy. Vy is equals to q tau divided by m into E phi minus q tau divided by m. Vz is equals to q tau divided by m into Ez. This is represented as equation 9. Using equation 1 for all components to solve equation 9 for Vx, Vy and Vz in terms of components of E and Bz, we obtain Jx is equals to sigma divided by 1 plus omega into tau square multiplied by in brackets Ex plus omega c tau into Ey. Jy is given by sigma divided by 1 plus in brackets omega tau square multiplied by Ey minus omega c tau into Ex. Jz is equals to sigma into Ez. This is represented as equation 10. Here sigma becomes equals to nq square into tau divided by m. This is given as equation 11, and omega c is q into bz divided by m. This is given by equation 12. Tau here is termed as relaxation time. The angular frequency omega c is called cyclotron frequency, and represents the frequency with which a charge rotates within the magnetic field. Thus, it denotes the measure of the field strength. The experiments can be categorized as A weak field limit, B strong field limit depending upon the value of omega c and tau. For weak magnetic field and or short relaxation time, omega c tau is much less than 1. The experiment is considered to be weak field limit. Whereas for omega c tau greater than 1, the experiment is considered to be in a strong field limit. Several materials behave differently under weak and strong field limits, for example, aluminium. However, while considering the single type of charge carriers, weak and strong fields are not considered separately. The above discussion considers the electric current to be an outcome of charge carriers moving independent to each other and respond to the applied field as classical particles. However, electrons are fermions or quantum particles and behave like waves. When we consider electrons as quantum independent particles that move freely rather than freely moving classical independent particles, there is a slight variation in the results obtained thus far. While considering free electron quantum gas, the obtained Hall coefficient is 1 by n cube, same as the classical case, along with the nil magnetoresistance. The difference is results in more evident when a more realistic model for solid material is considered, for example, crystals. Since the atom in a crystal are positioned in a periodic lattice, the electrons experience a periodic potential while moving through a lattice. This effect is strongest for the valence electrons or electrons present in the outer orbital of atoms, and particularly valence electrons for those de Broglie wavelength approaches the space of the periodicity of the potential. The allowed energies of the valence electrons with the periodic potential include a set of energy bands having gaps in between them. If the number of valence electrons per unit cell of a crystal is exact enough to fill a band, a solid is a poor conductor because by symmetry, the momentum states at each energy state will be occupied. These momentum states point in opposite direction for conduction. The electron should be able to jump a gap to reach a vacant state. When these gaps are big, high energy is required to jump them. This is the case for an insulator. On the other hand, when these gaps are small, room temperature thermal energy can cause sufficient electrons to jump these gaps, which is the case for the semiconductors. However, when the electrons are not enough to fill a gap, thus there are several vacant momentum states which can be filled by electrons. Such a material becomes a good conductor, for example, metals. Type of conduction is strongly affected by the shape of energy surface, that is, the band structure. The electronic states which have energies near the bottom of the band or the lowest lying allowed states act as free electrons only with the exception that they respond to the applied field like a lighter or heavier particles. Thus, the mass of electron m changes to the effective mass m star. Quite interestingly, the electrons having energies near the top of the band behave as the particles having negative mass. This means that when a field is applied, they oppositely accelerate the free electrons. For simplicity, let us consider these particle states as behaving like positive charge, and such states are known as holes. Alternatively, the periodic lattice diffracts the electronic states with wave numbers near the extremes of the band, similar to the diffraction of light waves from a grating. This implies that the motion of the electron wave is highly modified, sometimes reversed, similar to the manner the light of a specific color is reflected by a grating at specific angles. Since semiconductors have small band gap, thermal energy is enough to excite electrons to jump the band gap. This results in creation of electron-like state near the bottom of the upper band and the hole-like state near the top of the lower band. Both states carry current and the hole-like state act as positive charge. The number of these current-carrying states exhibit an exponential dependence of temperature, that is, varies with the Boltzmann factor as exponential of in brackets minus Eg divided by kT, that is capital T. Here, Eg represents the energy gap. The simultaneous existence of electron and hole states forms the basis of two-band model of Hall effect. Let Re be the Hall effect for electrons and Rh be the Hall coefficient for holes, as represented in equation 6. When sigma is equals to sigma E plus sigma H, where sigma is the conductivity of electrons and sigma H represents the hole conductivity as expressed in equation 11. Thus, the total Hall coefficient, that is Rh, is equal to sigma H square into Rh plus sigma E square into Re divided by in brackets sigma H plus sigma E squared. This is represented as equation 13. In this relation, m is replaced by m star, effective mass, and charge q is considered to be positive for holes and negative for electrons. Equation 13 can be obtained from equation 10 for weak field limit in brackets or omega tau that is much smaller than 1. For conductors, a charge carrying mobility mu is given by modulus of q tau divided by m star, that is represented as equation 14. For two-band model, conductivity can be expressed as sigma is equals to mu e modulus of qe into ne plus mu h into modulus of qh into nh. This is represented as equation 15. Also, the Hall coefficient for weak field limit becomes RH is equals to 1 by modulus of Q multiplied by NH mu H square minus NE into mu E square. This is divided by, in brackets, NH mu H plus NE mu E squared. Here, magnitude of the charge is assumed to be equal for both electrons and holes. In case of metals, the density of charge carriers as well as the sign of Hall coefficient depends upon the energy band structure of the metals. Alkali, that is lithium, sodium, etc., and transition metals like copper, silver, etc., have negative electron charge carriers with the charge carrier density of 1 electron per atom. In this case, in equation 6, can be used to obtain the Hall coefficient. However, in case of semiconductors, the band structure gives rise to both negative electrons and positive holes as charge carriers, and both contribute to the overall electrical conductivity. The charge carrier density is dominated by doping at room temperature, and thus either electrons or holes are prominent conductivity contributors. However, at elevated temperatures, there is a thermal generation of electron-hole pairs, resulting in significant enhancement in the conductivity since both type of charge carriers conduct. In this case, the expression of Hall coefficient is rather complex, and equation 16 needs to be used here. As a matter of fact, the density of carriers in a semiconductor is much lower than the metals. Therefore, VH is higher in metals for a given current, magnetic field, and film thickness values. Recently, the quantum Hall effect has been illustrated in very thin films at low temperature and high magnetic field conditions. Quantum Hall effect is more prominent in extremely small objects and very low temperatures. In these conditions, the energy levels become quantized, owing to splitting of energy levels takes place in very small structures, and the low-lying states they get filled at low temperature. Rather than varying linearly with Bz, the Hall resistance, that is V by I, demonstrates the steps with increase in in B in Bz, and the values of resistance at the ith step is h by e square, where I is an integer. The reciprocal of Hall resistance or Hall conductance increases in integral steps. The term E square by h is known as fundamental unit of conductance. In addition to this, fractional quantum Hall effect has recently been demonstrated, wherein the conductance increases in fractions of E square by h. This type of behavior requires theory beyond quantum confinement effects. Hall effect. Hall measurements by van der Pauw method. A charged particle, exemplar electron, inside magnetic field encounters a force, that is a Lorentz force, which is proportional to the field strength and velocity with which it travels in it. The force is maximum when the particle moves in the strength normal to the magnetic field. Maximum force is equals to Fl is equals to qvb. Here q is the coulombic charge of the particle, v is the velocity in centimeter per second, and b is the strength of the magnetic field, Wb per centimeter square. The application of current I on the semiconductor piece leads to the uniform flow of electrons through it. Velocity v of the electron is given by v is equals to I divided by n aq. Here the n is the density of the electron, a is the cross-sectional area. An external magnetic field perpendicular to the current applies Lorentz current to the semiconductor and results in accumulation of near one edge of the sample, that is figure C. Lorentz force experienced by the electron is Fl is equals to Ib divided by Na. The accumulation of charge at one end of semiconductor creates an electric field across the sample, shown in figure D. The resulting potential difference across the sample is termed Hall voltage, that is Vh. Interestingly, the current flows along the material, indicating the Lorentz force is balanced by the force on the electrons and the applied electric field. Strength of this electric field can be given by the following equation, where epsilon is equals to Ib divided by Qna. Hall voltage can be calculated by multiplying the electric field with the sample width, and Vh is equals to W epsilon. This is again is equals to Wib divided by Qna. This is also equals to Ib divided by Qnd. Here d represents the sample depth, as sheet density Ns is nothing but the electron density multiplied by sample depth. Hall voltage can be written in terms of sheet density as Vh is equals to Ib divided by Qns. Hall probe and measurement. Hall probe is an instrument of measure strength of magnetic field. The measurement of large magnetic fields is often done by Hall probe. It is a metallic strip which carries an electric current from left to right. The working of the probe can be summarized as a magnetic field perpendicular to the direction of the current flowing in the probe is applied. Consequently, the charge carriers no longer move from left to right in the probe. Second, the Lorentz force causes positive charge carriers to move upwards, while applying negative charge carriers are pushed downwards. This separation of charge carriers induces an electric potential across the probe. And finally, third, this potential varies with magnetic field. This potential is known as the Hall voltage and is measured by Hall probe. Any variation in the magnetic field can thus be detected by the Hall probe. The Hall probe includes a compound semiconducting crystal like indium antimonide supported by aluminium backing plate and encapsulated inside the probe head. Probe handle is perpendicular to the crystal plane. When Hall probe is placed such that the lines of the magnetic field pass at right angle through it, the meter reflects the value of magnetic flux density. The current flowing through the crystal, when it is placed in the magnetic field, develops a Hall voltage. Hall effect can be observed in a current when it is moved in a uniform magnetic field. Movement of charge carriers forces magnetic field to apply a Lorentz force on them. This results in the charge separation with an accumulation of positive or negative charge on the bottom or the top of the plate. The probe handle is usually made up of non-ferrous material, therefore does not disturb the field. Therefore, calibration of Hall probe is required with known values of the field strengths. In solenoids, Hall probe is positioned in the center. So students, let us now summarize what we have learned in this module. In this module, we studied about Hall effect and how it affects metals and semiconductors. We looked into experimental background and theoretical aspects behind the Hall effect. We developed an understanding about differential behavior of charge carriers in metals and semiconductors. In the end, we learned about Van der Pauw method to experiment. So students, let us now summarize what we have learned in this module. In this module, we studied about the Hall effect and how it affects metals and semiconductors. We looked into the experimental background and theoretical aspects behind Hall effect. We developed an understanding about differential behavior of charge carriers in metals and semiconductors. And in the end, we learned about Van der Pauw method to experimentally determine the Hall effect. Thank you.